Hello again. As promised, here is Math 2231, Alternative Delivery for 26th of March, Part 2. The overall objective of this part is we're going to discuss Newton's method. You might recall this picture that I've shown you many times, and the net result of this was that g, the derivative, isn't too different than the function itself, and that really is at the heart of what Newton's method does as well. So again, this is a very meaningful chart as far as I'm concerned. Okay, so let's suppose we want to approximate a solution to f of x equal to 0. And sometimes that can be very difficult, as you know. And suppose that we somehow have found a guess, an initial approximation, say it is some point x0. Now this initial approximation probably is not all that good, in fact being nothing more than a quick guess we made, and we'd like to find a better approximation, but this is easy to do because what we will do is we will be looking at, and this is the thing we're seeking, is the root over here. And so we'll say here was our x0 guess, but we'll say, oh, the function, the blue thing, is not that different than the red thing, which is the tangent line. And so we're going to use the red thing to approximate what happens with the function. And we'll say, oh, if I draw that tangent line, one might expect that x1, where that tangent line hits the x-axis, would be much closer to the root than our initial guess. And if we take that second guess and we draw another tangent line, we'll get x2, and that should be closer still. If we do it a third time, we get closer still. So that is the idea behind Newton's method. Now again, we're trying to solve for f of x equal to 0. So we're going to take this tangent line and set it equal to 0. But you see the other point that it's going to be, one point is x0, f of x0, the other one is going to be x0 comma 0. So when I plug x1 into, when I solve for x1, I guess I should say, what I will get is that I'm putting x1 in for x, and I'm putting 0 in for y, because this point is x1 comma 0, and it is on this line. So the y is 0, the x is x1. So I can solve for what x1 is, and I find out that x1 has to be x0 minus f of x0 all over f prime of x0. And again, we're just running fast and loose and saying that, oh, that derivative, let's pretend it's not 0, at least for now. But then the next one, what we're going to do is we're going to plug in, and if we do that again and we say, where does that hit? That new tangent line hit the axis, we're going to be able to find out an x2 point, which is x1 minus f of x1 over f prime of x1. Again, we don't want that to be 0. This gives rise to what is known as Newton's method. And so it is a recursive algorithm. That means if you know x0, you can use this to find x1. If you know x1, you can use this to find x2, and so on and so forth. So if xn is an approximate solution to f of x equal to 0, then the next approximation is always given by this recursion formula. So that's something you want to commit to memory, because you will be using that in what follows. So let's look at a first example. We're to use Newton's method to develop an approximation to the solution to cosine of x is equal to x that lies in the interval 0 to 2, and find the approximation to 6 decimal places. Now, I originally, when I made this slide, thought I'd have you pause and try to work on this. I'm going to go straight through. The first thing we want to do is we want to change this so this is f of x equaling 0. So what I'm going to do is, instead of saying cosine x equal x, I'm going to say cosine x minus x equals 0. So that's the equation we're trying to solve, and we're trying to find a solution that lies between 0 and 2. So let's just go ahead straight to consideration of this. Okay, so let's just begin. Since we know it's between 0 and 2, let's just guess that it's the midpoint. We weren't giving any value for this, so we just say x0 equals 1. That's our initial guess. And then we, like I said, have changed this into being this form. And so now what we can do is we can say x0 equals 1, so what is x1? Well, here's the formula. Here's the general recursion formula that we're going to use. This is what the derivative of cosine x minus x is. It is negative sine x minus 1. So this is the recursion formula. And we're taking x0 as input, and we're going to get x1 out of it. So when we do the calculation, we're going to put in 1 for x. That's 1 radian into your calculator, and we will get this as an approximation to the solution. You can see that we're hoping that that's a better approximation. At this point, we should point out that the phrase 6 decimal places does not mean just to get x1 to 6 decimal places and then stop. It means we continue until 2 approximations in a row are agreeing to within 6 decimal places, which is 1/1,000,000th. Okay, so if we're using that as a stopping condition, then we clearly need to go at least one step further. So now we're going to take this x1, this number, as the input, and we're going to calculate x2 using this recursion relationship. We plug in all the numbers and we get this. Notice that there was a significant change going from x0 to x1, a much less significant change going from x1 to x2. And so we're making progress. And we got the approximation to 1 decimal place. Let's do another one. And you really should probably do these calculations to make sure you're understanding of it. We get that x3 is this one, and x4 is that one. If you notice that these agree all the way up through, let's see, wow, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Actually, that agrees to 9 decimal places. And so we can say, wow, that's close enough for much work, and so we have that. Now, here's what is the truth about Newton's method. If the sequence of xn converges, it converges very rapidly. This is a very powerful technique, and many of the techniques that people use today are very close to this technique that we're studying right now. Now, this is example 2, and this is from your textbook, actually, and it says find the x-coordinate where the point y equals x cubed minus x crosses the line y equal 1. Now again, we're not solving x is equal to 0. We want to find when does this line, when does this curve cross that line. So what we're going to do is we're going to take this difference of the two, and that's going to be set equal to 0, and we're going to go through and do the calculation. I am going to ask you to pause on this one, try to do the problem, and see how you do. Let's see how you do. Okay, so this is the table from your book that you might have ended up looking at. Notice again that we did change this, so we're really talking about subtracting that, and that's a mistake students often make. And we build a table, we let n grow, and we see that n gets closer and closer, and we get a very significant agreement in only 4 or 5 steps to the root. So again, when it works, it's a very powerful technique and works very well. Let's look at another example. I know this one's called example 2, but this is the second example 2. And we want to use x0 equal 1 to find an approximation solution to the cube root of x equal to 0. Now I realize that you can kind of say, oh, I could solve that anyway, but let's watch what happens with Newton's law. So pause, do some work, and come back, and let's see how you did. Let's see how you did. Well, we start with this, and we start getting the recursion relationship, but watch what happens when we do this. Our initial guess was 1. x1 ends up being minus 2. x2 is 4. x3 is minus 8. x4 is 16, etc. In this case, the method fails, and fails spectacularly, just like I talked about the second derivative test could fail. Okay, so either it works really well, Newton's methods, or things go pretty much straight to hell. Moreover, sometimes Newton methods can converge if you aren't really careful about your initial point. It might converge to the root, not the root you had in mind, but another root of the function. And this is talked about a little bit in your text, not very much actually. This gives rise to one of my truisms I think I've learned over my life, and that is the fancier the technology, the better it works sometimes, but is often much more fragile than more old school techniques, and you have to be careful in using it. Okay, so where are we now as we're approaching midterm? Well, chapter 2, we've done complete of chapter 2. We've also done the complete piece of chapter 3, and we've almost done all of chapter 4. And a lot of the stuff came together, but it certainly has come together. In fact, we've done everything except talking about a gadget called L'Hopital's rule, which will be my first topic after the break. And my second topic after the break, which will happen in the very first class that we have, is we will begin talking about antiderivatives. So, after the break, we only do chapter 4.5 to finish the derivative intensive portion of the course. With chapter 4.8, your mathematical life becomes instantly twice as complicated, but twice as rich as well. A transition quiz posted in your syllabus tab will be due on Tuesday. We return to class. You don't have to do it until Monday, but we will self-report and grade it on Tuesday in class. As I say, it will be self-reported and self-graded, and this is to me, I think this is an important transitional step to what is happening on the flip side of spring break. And the quiz looks something like this. It's in your syllabus tab, so look at it on Monday, if not before. Now, more than ever, time is precious. Each day must count. Doing the math will make you strong. See you after spring break, and thanks for being flexible. Take care.